Good morning, everyone, or good afternoon, depending on where you are joining us from, and welcome to today's webinar. My name is Cess from Business Review, and I will be your host. It is our pleasure to have INNIO Jenbacher North America with us today, who will be presenting this webinar entitled Microgrid Solutions. Today's presenters are Robert Ottengruber, Senior Product Manager, and Greg Gonzalez, Senior Sales Manager. Before we begin, I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please click on the link that you received via email to rejoin the session. If you have any questions, you can send them in via the questions widget. Just type them into the box at the top right-hand corner of your screen and click Submit. We will allocate some time at the end of the session to address any questions or thoughts that you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. Now, please allow me to welcome Greg.
Thank you, Seth. Again, my name is Greg Gonzalez. I'm a Senior Sales Manager for Oil and Gas in North America. And the whole microgrid thing is obviously spreading into that vertical market as well. And we're excited to have everybody online today to give you the latest and greatest from the Jenbacher's point of view. Here we go. For the agenda, initially, what I'm going to do is basically go over the different platforms, engine platforms for the company, and give you a basic description of where we are in each power node from our 2 series all the way up. We'll actually touch on the 9 series today as well, but since this is a North American crowd, for all practical purposes, that particular package isn't available at 60 cycles anymore. So basically, we'll be focusing on the Type 6, Type 4, Type 3, and Type 2 engines. With regard to our installed portfolio globally, we're somewhere in the area of 37 gigawatts currently delivered and deployed. And of that amount of power that's installed, 60% of it is actually connected to our myPlant system, which is an integral part of our maintenance and monitoring program that really from an operational standpoint plays a huge role in us being able to monitor the engines and being able to extend life to overhaul as much as possible. But as you can see from the slide here, we're over 25,000 engines delivered. Theoretically, if you look at 37 gigawatts, it's about 60 million homes. And that's about the power, it's about 1.5 times all of the homes in Germany at this point. So that's just a little hypothetical note to give you an idea of scale of how much power we have deployed. As far as the engine power node range, we're from 250 kilowatts up to 10.6 at 50 cycles. And again, that's including the 9 series. Typically in North America, we go to about 4.5 in the 624. So again, durable product. We've been in the power generation game for over 65 years. We're constantly adding new products such as fast start capability, fuel flexibility, and we'll talk more about that in reference to the hydrogen product and the hydrogen fuel source, which is going to be moving forward, pretty integral part of the microgrid and distributed energy market. To give you an idea of scale, this is everything from the Type 2 all the way up to the 920 FlexGen. But what I really want to focus on is the Type 6 and the Type 4 primarily. Those are kind of the backbone of our fleet at this point. The Type 6 comes in a V12, V16, V20 configuration, as well as a two-stage turbo V24. And the J624 is our 4.4, 4.5 megawatt unit. And for some of the larger applications, it's a kind of a unique node in the industry with regard to power. It's something that's gaining popularity, gaining traction in the States. I know that. And it's basically a good size for a power plant, if you will. It's got some flexibility to it, but it still has enough size and heft to it if you're looking for a 25, 30 megawatt solution. As far as the Type 4 engine, this is our first engine that offers an 1800 RPM engine, whereas the Type 6 is a 1500 with a gearbox. That's kind of a feature of ours in the market. But the Type 4 is an 1800 RPM engine, and this particular platform is actually 100% H2 ready right now. And you will see some deration with the H2 fuel source, but it is 100%, whereas the rest of the engine line, excluding the 920, will tolerate a blended fuel of natural gas and hydrogen. As far as the Type 3, again, 1800 RPM engine, we're about 500 kW to 1 megawatt. Good electrical efficiency at 43%. It's a pretty strong engine in that we have over 11,000 of those in the field. From my perspective in oil and gas, this is the, if you will, the drill rig engine for the company. And we've seen a lot of the 320s, the 20-cylinder version of the Type 3 deployed in drill rigs. So that's a strong engine type for us. And then the Type 2 is the smallest engine at 250 to 330 kW. Again, in the 40% electrical efficiency area, we've got about 1,300 of those running in globally at this point. So it's a pretty strong portfolio. It's a broad power range, and I think it fits well into the microgrid distributed energy industry. Again, this is just another chart showing the power range for each unit. It also shows the optional H2 pipeline gas combination that you have, and with the different blends on the different engines. For instance, 60%, you can have 60% natural gas with the balance of H2 in the Type 6. As I mentioned, in the Type 4, it's 100% hydrogen capable. So that's something that I think we're an industry leader in that regard. In fact, I know we are. And then the different blends of fuel in the other Type 2, Type 3 engines. But this will give you an idea of where we are and what the targeted dates are for 100% H2. And we're pretty much targeting 2025 for the product line to be fully capable for H2. With regard to product support and life to overhaul, if you will, we have an overhaul program, kind of a swing program, where we can actually take engines, have an overhauled engine ready to go for a client, and basically do an engine swap. And typically, we're looking at the 80,000 hour range for a major overhaul at this point. And we actually have in the works at this point overhaul capability being developed here in the States. Typically, everything would go back to the factory in Jenbacher, but we are developing first a component rebuild center in Waukesha, Wisconsin, and that will eventually evolve into a complete engine overhaul facility. So I think that's going to really enhance the speed in which we can turn engines when they're finally due for their first major overhaul. As far as just a basic sustainable combined heat and power application, this is an example of a typical application for an energy consumer, showing you the high efficiencies of capturing both the electrical power and the thermal energy off of the engine. This gives us somewhere in the range of almost 90% total energy efficiency. And that can be derived in terms of hot water, low pressure steam, processed steam, really however you want to use that heat. We can adapt a system that will be quite effective in the 6 and really in all of the engine types, but we tend to focus on the 6 type for this kind of application, just because of its power node, basically. With regard to decarbonization, what we see here is the U.S. average, grid average, in reference to grams per kW hour. And this is broken down by basically the fuel types in liquids, coal, natural gas, gas turbines. And as you see here in the to the left side of the slide here, there's a direct correlation between the combined heat and power efficiency as it affects the total decarbonization or CO2 footprint, if you will. So if you're able to capture that 90% fuel utilization, the 90% efficiency in reference to fuel use, you'll see that the combined heat and power is the most significant in reducing the carbon footprint. Again, the U.S. Grid average is somewhere around 400. You can be almost less than half of that with a combined heat and power configuration. As far as the energy landscape globally and in North America as well, obviously, there's a series of pretty specific challenges that I think all the equipment manufacturers are facing, and I believe that INNIO is in the lead in reference to being conscious of the high efficiency, low emission decarbonization process, and that's really what we're focused on moving forward throughout our engine platform portfolio. The challenge, basically, it's the 3Ds in electrification here is the decentralization or the shrinking of power systems to a distributed energy configuration, and then the decarbonization, including the combined heat and power to drive that decarbonization down. That's something that we're very focused on from a technical perspective. Digitalization, that's basically driven by the mission critical space. In terms of data center, cloud storage, obviously that capacity, that vertical market is, I would say, growing almost exponentially globally. It's a vertical market that we continue to pursue. We have people assigned specifically to that, and that's an exciting vertical market. So we're excited about being able to provide the resiliency and the reliable power into the data center space. And then, of course, electrification. In my segment, which is oil and gas, we see a tremendous amount of electrification. Something that's been an overwhelming opportunity for us has been the e-frac market. We're working with several e-frac companies to develop their e-frac, both stationary and mobile fleets. And we're having pretty good success with that so far. But along with the drilling rigs, the J320 that I mentioned at 1 megawatt, it's becoming a more popular option as oil service or drilling contractors, energy services companies make the transition from diesel over to electrification or natural gas generators. So it's something that's a pretty exciting opportunity for us at this point. With regard to some of the additional challenges on the landscape, obviously we need stability and resilience on the grid here in North America. Lower cost of distributed power. I think that that's coming along as the need rises, and we all know that the utility, the grid itself, is being stressed more and more, almost on a daily basis, with the electric car charging and just additional load, everything being electrified. So we feel like we'll be a cost leader in that arena as far as distributed power, microgrid power, that kind of thing. And then the regulations that we and all the other manufacturers have to deal with in reference to emissions, EPA standards. We work very closely with our clients to provide and specify the appropriate OxyCat or SCR system, whatever is appropriate for the application and the ambient conditions that the customers find their equipment in. So that's something that obviously we have to address as well. And then this is just some of the headlines, why microgrids? Obviously the weather, extreme weather events, hurricanes, again, the overloading of the grid to a point where there's rolling blackouts. I think the Californians wrestle with that a bit. I very clearly remember the Texas power outage of about a year and a half ago. I was living in Dallas, and I've never seen anything like that in terms of an ice storm and cold snap in Texas. So it opened up a lot of eyes to the issue of grid resiliency and the opportunity to basically explore generated or distributed generation to include microgrids with several different energy sources involved. So it's an exciting time to be in the power generation industry. Again, just aging power grid resiliency. This is something that we think the distributed power and the microgrid industry is really on the cusp of truly taking off. And then basically, what are microgrids? I think everybody has a pretty good understanding of what a microgrid system is, but I'm going to give you the INNIO version, the Jenbacher version of how we approach the market here.
Yeah, thank you, Greg. My name is Robert Altengruber. I'm product manager of phone controls and microgrids. And now we talked about the major trends of the energy transition and also the need for resilient and economic solutions. And in this section, I would like to show you how the microgrid can support the energy transition. And we'll also have a closer look on the principles of a microgrid controller, also what the benefits are, and we'll also talk about how microgrids can be optimized. But let's first start with the definition of the term microgrid. What does it mean? So microgrids are small-scaled power generation and distribution systems that can contain loads, including thermal loads as well. And they are so-called DERs, meaning that distributed energy resources, which can be engines, renewable energy sources, and also storage systems. Microgrids can always be operated isolated, but most of the time also connected to the grid. Plus, they can also seamlessly switch and transition in between. Typically, the microgrid size is around between 100 kilowatt and 10 megawatt, but there are also exceptions to that. And in the past, microgrids were predominantly used for grid access or backup power. Now that really changes. They are more focused on resilient and sustainable, also economical solutions supporting the grid. And in some cases, they can also be alternatives to the public grid even. As you know, the renewable energy resources as PV and wind, they are volatile by nature, right? So this is why the gas engines play really an important role here as a dispatchable power, providing that balance and inertia that it's so much needed for these systems. operated with renewable gases and also hydrogen in the future. These gensets are a solution to the challenge of combining resilience and sustainability in a single distributed energy resource. And as a result, the gas engines are key to provide the secure and affordable and also green energy when the renewables are not available. And by adding this stability, the dispatchable gas engine even further allows the further adoption of the renewables, right? So on this slide, I would like to show you the differences between classic island mode operation, hybrid solutions, and also microgrids. So there's the classic island mode operation, where you would have one or more gensets that could run grid connected or in island mode. The controls of such applications are pretty basic, but also very resilient. And we do have lots, or let's say thousands of installations worldwide, which are island mode capable already. Then there is the hybrid microgrid. This is where when the gas engine, for instance, is combined with another renewable energy source, such as PV, for instance. Then without the centralized management, such installations can already become quite tricky from a controls perspective, as the renewables are volatile in this system, and the engine has to balance the load swings. And finally, we have the typical microgrid scope with dispatchable distributed energy resources, like the gas engine or other renewable energy resources in the mix, as well as storage systems, right? And all of them managed and orchestrated by a centralized microgrid controller. So now that we know what microgrids are and why they are needed, let's have a closer look on the INNIO approach for microgrids, starting with the microgrid controller. The microgrid controller is located on site, and it builds on the already proven Jenbacher master control system, and it's, so to speak, the brain of the microgrid. It's optimized for Jenbacher solutions and Jenbacher assets, but it allows the integration and of a wide selection of different distributed energy resources, such renewables, storage systems like battery storage and also thermal storage. And we are supporting the various known standard bus protocols as Modbus TCP, for instance. As you know, microgrids can be connected to the grid and operated in island mode as well. In island mode, the microgrid controller's highest priority is always power reliability. And it does that by maintaining the frequency and the voltage for all the given load scenarios. And it optimizes the use of the different distributed energy resources connected to the system to prevent an outage. In the unlikely event of an outage, the microgrid controller and the Jenbacher gensets are also black start capable. Now with the microgrid controller, we ensure the resilience of the system, but we also want to optimize the economics. And in many cases, the microgrid is operated grid connected most of the time anyway. And this is really where the Jenbacher solution shines and stands out with the myPlant optimization. The myPlant optimization is an AI or machine-based learning solution that takes a holistic approach, improving the operational profitability of the entire plant portfolio, from the engine to heat pumps connected, to the storage, to the PV system, to the battery. And it also takes all the customer-specific operational requirements and annual targets into account. So as long as the microgrid is grid connected, myPlant optimization can optimize the plant. And as soon as there is an outage, it seamlessly transitions into island mode operation, and the microgrid controller takes over again and ensures stable operation in island mode. So let's have a closer look at the benefits. First is renewable integration, as mentioned before already. So by providing this resilience, the microgrid really enables the renewable adoption, lowering the emissions and energy cost. Next is peak shaving. With the use of a battery storage system and import-export control, the microgrid can also reduce the peak loads and therefore also demand charges. Reducing the maximum load also helps then the grid infrastructure. Then we have energy arbitrage. So when the microgrid is grid connected, you can use real-time price arbitrage, meaning charging and discharging the storage depending on the electricity price, and by that further improve the economics of the microgrid. Then there is power reliability and islanding, very important one, as this is the main purpose of the microgrid controller. And it's to maintain the stability of all the distributed assets in all operating conditions. And it also allows for the seamless transition in between, as we talked about already. Then we have spinning reserve. In the old days with an island mode operation with high load fluctuations, typically there was a spinning reserve that was an engine required to ensure additional power is available when needed. With the use of the battery storage now that can provide instant power, such idling gensets are no more required. So that's also a benefit in some scenarios. Then providing ancillary services. Well, the microgrid is not only providing resilience in case of an outage, it can also support the transmission grid by facilitating demand response programs, which in the end helps to prevent blackouts from happening. And last but not least, we have the optimized self-consumption. That's a big advantage when you have a battery, for example, when you have surplus energy from renewables and feed-in tariffs are low. It's better to store the energy and use it at a later stage when the energy prices are higher. So it's similar to the energy arbitrage. So let's have a closer look on the microgrid controller itself and how it works. As said before, the main purpose of the microgrid controller is to provide the resilience in all the operating conditions. And to do that, coordination of a centralized control system is required to manage the combination of all the renewables, the electric storage units, and the Jenbacher engines most effectively. With the latest software of the microgrid controller, we can support up to 50 distributed energy resources that also can be configured individually to fit the desired plant-specific application requirements. There are various distributed energy resource types supported. Of course, Jenbacher engines, but also existing third-party gensets and a brownfield installation, for instance. Of course, we support renewables like PV, wind, or hydropower as well. Electric storage systems as battery storage systems, ultracapacitors, kinetic energy storage, supercaps. Also power to X, so power to heat and power to gas. And of course, we can also integrate the good old-fashioned diesel backup generators. We can integrate other assets as well. But that's mostly on customer demand. So if you have a project where you would have another asset, then we can have a look together and probably integrate that one as well. So how does the microgrid controller control the different energy resources? So first and foremost, it does that by controlling the active and reactive power. It does that by controlling the frequency and the voltage droop of all the connected assets. And the mechanism behind is that if the frequency drops, as you see here on the graph, all the DERs connected, so all the resources connected, will increase the power instantly. There's also import and export control. This is an essential function for behind the meter optimization and also peak shaving. and also for maximizing the self-consumption. There is load management and DER priority. So while ensuring the power is available as needed, the microgrid controller also determines the priority of the DERs to fit the actual need in terms of availability, operational costs, what are the service schedules, the reliability of each of the assets, and the block load capacity to provide the required stability to the system. There is also state of charge control that ensures that there are enough energy resources for resilient operations. So by state of charge, we mean the storage or the capacity state of charge of the battery storage system, but it also reserves capacity for economic optimization, right? The importance of hybrid system optimization, that's something that we learned developing the microgrid controller, is how important it is to optimize the interfaces between distributed energy resources for latency. Especially that's applicable for the BSS system, for improved transient performance, and also switching between grid parallel and island mode operation. That's really crucial. Hybrid backup power supply, that's really impressive because the battery storage system, if there is one, can provide instantly power in milliseconds, giving the gas engine time to start up, even if it's not preheated. So it's also lowering the cost from that perspective. So here you can see the user interface of the microgrid controller. If you have an XT4 transit controller or master controller system, this might look familiar to you, where we have such a couple of screenshots here to show a little bit better how it looks like. So we have the main microgrid overview, where you see all the different assets. You see the status in a single line diagram, all at a glance. There's also a dedicated screen for the state of charge control of the battery. So the state of charge control can be optimized by myPlant, but as you see here, you can also adjust it manually in the microgrid controller. And for each of the distributed energy resources connected, there is also an asset overview, which you see here on the bottom. This, for instance, is a battery storage system here. I already explained how myPlant optimization takes a holistic approach on optimizing the entire plant. And before we continuing with the optimization features in more detail, I would like to highlight that myPlant optimization is also based on the existing myPlant ecosystem, a system that has proven to be robust and scalable over the last decade, and with almost already over 11,000 units connected, proving the scalability of that system. So highlights of the myPlant optimization. So first, there is an energy dashboard with all the information and overview that you need for the different assets, their connection, and also their status. It also has a separate dashboard showing the past and the forecasted cost savings generated by the optimization itself. And the core functionality is really the economic dispatch with smart optimizations that considers all the energy generating assets, the properties, to meet the demand, the energy demand at the lowest cost possible, given all the operational yearly and daily constraints that you might have in such an operational plant. It also supports dynamic market data through APIs, but also allows the input of power and gas price manually in the systems, and also supports time of use prices. Then, of course, very important for the renewables is also the weather forecast, which is integrated already worldwide, including the solar radiation data. And we have also battery storage control, so state of charge control as well, similar as on the microgrid controller. And it also supports different battery chemistry and types in terms of charge and discharge cycles supported. There's also heat optimization, and I think this is where we really differentiate from some of other solutions. As manufacturer of CHPs, heat optimization was always a focus from the very beginning. So it's really built in and not bolted on. And of course, we also have support for import and export controlled and enabling peak shaving as well. So here you can see myPlant optimization at work, where the AI generates an operational plan of all the energy resources and storage systems to meet the electrical demand and also the thermal demand at the lowest cost. So here you can see a screenshot or graph from our facility in Jenbach with two Jenbacher CHPs. We have one J420 and we have one J612. We have a power to heat module and we have a battery storage system. And in the blue line, you can see state of charge of the battery storage systems, where we have about one to two charge cycles on the battery, optimizing the self-consumption and also enabling energy arbitrage. So myPlant also provides not only the weekly and daily planning, but also provides a yearly forecast that is continuously updated with the newest data available. So now we covered the theory, and let's have a closer look on a real microgrid with the microgrid in the INNIO 360 Energy Lab facility in Jenbach. The microgrid there enables us to simulate and verify all the different possible customer requirements that might come up under real market conditions directly at site in Jenbach. So that has been very helpful for us developing projects. It features a fully integrated microgrid, also for us to increase the resilience of our production facility, as well as lowering the energy cost. And of course, it also lowers our carbon footprint. And all of it, of course, managed by myPlant optimization on top. So here you see the microgrid at our energy lab. We have two CHPs, one with 1.5 megawatt and the other one with 2 megawatt type 612 engine. We have two heat storages with each 10 megawatt hour storage. We have two thermal boilers with 2 times 8 megawatt. And we have one power to heat module. And also we have a battery with 1.2 megawatt hours and also with 1.2 megawatt in power output. So it's a 1C battery. And we also have a small water turbine here installed. And we do have also, of course, the test bench, but it's not really included here in the microgrid, also not in the business case that I'm showing you because the load of those engines is not really plannable. So as mentioned, I would like to show you a simplified business case of the microgrid at our facilities. What we did not include here is the water turbine and the power to heat modules and also the central test bench, as said. And for the PV assumption for this business case is that we use the maximum power that would be allowed on our facility, which is 1.5 megawatt. In terms of energy demand from our facilities, electricity, we have 27.2 gigawatt hours yearly energy demand. Heat, we have so thermal energy, 15.3 gigawatt hours. And the average energy cost, that is in 2021, I have to say, was 207 euros per megawatt hour for the electricity and 50 euro per megawatt hour for the gas. So the business case shows the upgrade basically from our old heating facilities and transitioning it into a microgrid. The microgrid solution here is sized for maximum resilience with the two Jenbacher CHP engines that can meet the entire power demand and also heat demand of the system in the event of a grid outage. We have still two of the original gas-fueled boilers remained installed as a backup in case of low electricity but high heat demand. We do have the battery storage systems that we use for peak shaving, reducing the demand charges. All the benefits basically shown before, also enabling energy arbitrage with approximately 1 to 2 cycles, charge and discharge cycles a day. Yeah, and if there's a grid outage, the BSS also improves the island mode performance along with the CHP systems and provides for instant hybrid backup power at the Jenbacher site. Finally, the myPlant optimization enhances all of the distributed energy resources, including the storage for improved economics. With the microgrid solutions that we have now, the grid consumption you see here in the lower left side in the table, the consumption is now 62% from the grid consumption. Formerly it was 100%. The CHP provides 32% of the electrical power and the PV provides the remaining 6%, whereas the CHP provides 63% of the thermal power and the boilers are providing the remaining 37% of thermal power required. Overall, that led to 80% reduction in levelized cost of electricity for us. So let's look at the CapEx, at the investment. So previously, I mean, that was given, so there is no investment there, but of course we had to invest in the microgrid solution. That was around about 5.5 million euros for the CHP, the PV, the battery storage system, and also the control systems, microgrid controller and updates of remaining other control systems. But we could also reduce the operating cost by 1.5 million euros per year, which results in a payback period of 3.7 years, which is really great for a microgrid installation. So that concludes the microgrid presentation from my side, and I would like to hand it over to Kes for the Q&A session. Thank you very much for the attendance.
Thank you very much, Greg and Robert. That was an insightful presentation. Now we'll begin our Q&A session. Just a reminder for the audience, in order to ask questions, you can send them in via the questions widget. Just type them into the box at the top right-hand corner of your screen and click submit. In the meantime, let's start with this question from an audience member. What is midlife overhaul at 40k hours? Is this also swing engine based or overhaul kit at site?
So can you rephrase the question, or can you read it once more, please?
Yep, sure. So what is midlife overhaul at 40k hours, if this is also swing engine based or overhaul kit at site?
Okay. Yeah, I mean, there are 40k hours. That's basically the minor overhaul. It depends on the overall engine lifetime, right, which can be 60 or 80,000 operating hours. And we do provide overhaul kits, spare parts packages for an in situ maintenance. Yeah. But I think there would be also, if required, right? For instance, if you want to reduce the outage time, I think there are also possibilities to get overhauled engine or like kind of swap engines.
I think that I also think that the fact that we're going to be centralizing, first of all, the component rebuild here in North America, and then having that migrate or evolve into a full engine overhaul, I think that's going to speed that process up quite a bit because you won't have transit time back to Europe.
Okay, fantastic. On to the next question. So, how does coordination with other systems like PV or BESS work when it comes to planning or design level? What inputs or information is needed by INNIO to program and commission the microcontroller?
Yeah, thank you for that question, and that's really crucial in developing the projects and in the ITO phase, right? So of course, the aim is really to have a platform agnostic system to be compatible with all the different systems, but of course we have to look at the capabilities of the distributed energy resources, whether it's an old diesel engine, what are the interfaces, if it's another gas engine. For the battery storage system, the critical aspect is for sure the inverter capabilities, but also the interfaces provided. So this is really the most crucial in the planning phase.
Okay, fantastic. Another audience member has asked, can JB microgrid controller manage the heat flows or equipment in the system? Or is it just limited to the electric equipment connected to the microgrid?
Yeah, good
Please
question.
elaborate.
And, thank you for that question. Yeah, no, yes, definitely. It can manage the heat as well, and I think that's really the USB of the Jenbacher microgrid solutions. I haven't seen any other that is optimizing heat as well. Most of them they only do the electric side of it, but we have the full holistic view on the site because if you need to have heating, right, that's a constraint to the optimization piece. So definitely, yes.
Very interesting. And will maintenance be conditioned based when assets are being managed by myPlant?
I would say it can be. So as far I'm not aware of condition-based service offering right now, but myPlant can definitely be used with the predictive analytics, and there is also additional advanced sensor sets available, which can show you the remaining use of life of some of the components. So mainly it's consumables like air filters and oil filters, those kind of components where you can really already do condition-based maintenance. It's not yet. We don't have the sensor data available for all, especially for mechanical components, right? That's really tricky to have that fully automized, but we're definitely going into that direction.
Great. Just a reminder to everyone, you can still submit questions via the Q&A widget. Another question that's been asked is, does the microgrid controller require the use of master control?
Yes. So yes, it does, because the microgrid controller is actually a feature built on top of the master control. So it's basically the same cabinet as you're used from the master control. It uses the same XT4 system and hardware. The microgrid controller is basically a piece of software running in addition to the master control, enabling the connection to the renewables, the battery storage, But what has changed, of course, is how the different distributed energy resources are connected and how the load is managed. We mentioned before active and reactive power sharing in particular.
Great, thank you very much, Robert, for that answer. And this is a question from an audience member. They have asked, I admire Jenbacher's development of hydrogen-ready engines. Are there any emission concerns regarding increased NOx, or have these concerns been mitigated?
I would say that the concerns with regard to NOx could be taken up in any of our standard offerings for, SCR, oxygas, whatever after treatment is deemed necessary based on the if it's a blending of fuel. We would obviously have to know what that blend is and what all the fuel constituents are for us to tailor a solution for the application. Based on location and duty cycle, all of those things, but they can be mitigated for the increased NOx.
Great, thank you, Greg. And does Jenbacher engines work with microgrid controllers from other brands?
Yeah, it does. And that was very important for us, right? To be platform agnostic, that we can be easily integrated with other engine types. Also, we wanted to provide solutions for brownfield installations for existing customers, which might have other systems as well. And I think that's very important. Yeah.
Thank you, Robert. And here's our final question before we end our Q&A section. Can microgrid, including renewable, operate in island mode without battery storage?
Yes, it can. And I think we showed that already, which is the hybrid microgrid. But it has some challenges to it because the PV and the renewables are volatile. They are not really plannable. So they more kind of disturbing here are a little bit disturbing the frequency or basically act as a negative load, especially when there is a cloud coming or going away and there is sudden increase on PV power. This can have significant impact on the stability in island mode operation. And also the genset or the CHP is really providing in most of the cases those inverters, those PV inverters are not grid forming capable. That means the frequency is managed or kept by the genset. And in order to have a stable operation, the power share needs to be 2/3 of the whole power demand, which runs on the gas engine. As soon as the power is lower on the gas engine and higher on the PV or renewable, that can cause severe instabilities of the system. And the battery storage basically helps in that case because you have a kind of a buffer, and you with the PV, the renewable energy is stored in the battery storage system, and the battery storage system can somehow have inertia in it because the inverter is really grid forming capable, right? So it can somehow mimic the inertia of a gas engine.
Great. Well, thank you very much, Greg and Robert. And that's the end of our Q&A session. If you did not get your question answered, it can be answered at a later date. So that just leaves me to thank Greg and Robert for what was a fantastic presentation, and to INNIO Jenbacher North America for sponsoring this session. To the attendees, we would be grateful if you could please take time to fill in the short survey by clicking on the survey widget and you will also receive an email shortly telling you how you can access the on-demand version of this webinar. Or you can access this through our website, www.pmi-live.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned and follow us on Twitter at BRWebinars for daily updates and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.